Hi everybody, welcome back. Today we're going to set up a new board. We have to set up a schematic first, but we're going to kind of skip over that part and just kind of look at the parameters that go into a new board, at least from the fundamentals. So if we look down here, I've got a project. I'm going to set up a new one. I want it to be in the F400, the factory 400 one. Let's see. So I will, just like any other program, go to File and New. We have quite a few options. Today I'm going to skip project. That one, I have no idea why it exists. Maybe the folks over at Eagle would chime in and help me understand why in the world that's useful. But I want to create a schematic. I'm going to skip all the setups for the schematics. I'm just going to put a single piece on the board. So I hit Add Component. And this is just for a quick reference. I'm going to go pick some random part. I don't really care what the heck it is. How about a CD 4050? That's a fun one. Okay, cool. We'll put, I think this is a hex. Yeah, we'll put them all on there. Anyway, it doesn't really matter what I do there, except that I'm going to save that schematic. Automatically wants me to say, hey, where in the heck is that going to go? We're going to put that in our test things here. So let's see. How about we're going to do our fun board, and that's version A-V1. We'll go over versioning at a different time. All right, so we're going to bail out of this one. What we really want to see is the board setup. So I will click the generate switch to board. As soon as I click that, this is the first time I've done that with the schematic. So it says, hey, do you want to do that for real? Do you want to create from a schematic? I say yes. And it pulls up a fresh new board with all the little defaults. Put that little guy in the middle. So the first thing we have to figure out when we're setting up a new board is, there's a lot of things we have to figure out, but who is going to make it? What are the capabilities of the fabricator? Because there's some extremely important things to consider here. The first thing is it's useless to design a board that cannot be built. It's physically impossible to build it. And it's very helpful to design a board that is relatively easy to manufacture, because if you start picking features on your board and asking for things that are extremely difficult to manufacture, technically possible, but extremely difficult, the board houses will let you know that via the price that they give you. So, if I want to do some, a 16-layer board with all kinds of blind and buried vias and controlled impedance and all this other stuff, micro vias, because I've got a big BGA that I want to put on my fancy design. All of that stuff is perfectly fine, except that the cost of that board is going to be enormous compared to a simpler board. So let's take a look at some of those parameters, and we're going to take a look at a board manufacturer in China and kind of get an idea of what, how you pick out some of this stuff. Some of the technical details, you actually have to contact the board manufacturer to ask them, what a limitation might be, so you can define it correctly. So over here, now on a small monitor, this is kind of crazy. So this toolbar has, if you look at the top DRC, as soon as I move my mouse, that goes away. So I actually have no idea how to click that. This is like, I don't know if this is a bug or I'm doing it wrong or whatever, but at least I can pull this thing off and kind of drag it halfway onto one of my other monitors. What I'm looking for is this DRC. That's the design rules, and it pulls up. This is a default design rules page, so let's go over these things really quick. You essentially have to go through every single tab that you see here just to kind of make sure everything is going to be in line with your design intentions and the capability of the board house. So you can edit this description. This is just the default one that comes up. You can edit the description, and just like every other horrifying description, you have to deal with HTML. In this one, you don't get a proper text editor, and you can load and save these things off to different files. So I don't use the default one. I have my own files that I use, and maybe we can go over that soon, but let's go through the basics here. First, layers. Well, the first decision you have to make in your circuit board design is, how many copper layers do I need? The default here that it starts off with is 2 layers, sorry, and Eagle, at least my version, can go up to 16 layers. And if you haven't already noticed, layers go, they're even layers. You can't have a, I mean, I guess technically you could have a 3-layer board, but that would be a strange one. So they typically go in pairs. So let's say that this one's got 2. This one describes the how the material is stacked up. A circuit board is made up of a whole bunch of layers, not just copper. So it'll have copper, and then it'll have some fiberglass or whatever dielectric material, and then another layer of copper. If we go up to say 12 layers, you can see that there's how it's all stacked up visually, and these are all default numbers here, and the stack up in some boards, it doesn't really matter. You can use a default stack up. In others, like impedance controlled boards, or boards with big power planes or something like that, you may want to have different copper thicknesses and different cores and prepreg arrangements in here. That's a totally different discussion, is like how you determine your stack up from a technical perspective, but this is how you define it in Eagle once you know what that is. Via pairs is referring to how the vias are structured. So this right here is referring to the how a via, when you drop a via on any layer, it's going to go all the way through the board. And this is the standard way that a via is done, and it's the cheapest way to do it, because the board house will laminate all of these layers together and then drill them all and plate them and all that. So it's very easy. When you get into 10, 12, 16 layer boards with BGAs and all that kind of stuff, a lot of times you'll end up with blind or buried vias, and you define those by hitting this little plus. You can define a new via pair. So I want a via pair to go from 1 to 4. So it'll go from one side, but it'll only go to layer 4. So it won't, I can have other vias over here. So let's say I have another one that is going to go from, let's say 12 to 16. And okay. So now we have this other, so these are called blind vias because it doesn't go all the way through. And you can also have buried vias. I'm getting pretty close to making an impossible stack up, but that's not for today's discussion. I'm just going to show you how you define these things, assuming that they're actually physically possible or practical to make. So this is called a buried via. So you can have a via inside the board that you can't see from either side of the board. Really handy to design with all this stuff, but blind and buried vias at a huge expense to the finished board. So different discussion, but that's how you define them. So in the case of spacing, let's take a look at. I think we got some stuff up here. I pulled up some PCBWay stuff. I've used them before. They've done a great job, and you can see here that they have this capability section of their website. It has all this stuff about minimum traces. It's 4 mils, and that might be like, oh, perfect, 4 mils. That's excellent and easy. Not a problem. But if you look really closely here, it says strongly suggest to design trace above 6 mils to save cost. It's like, oh, that's an alarm bell. So if you go over here to the little quote thing, you can see right here, you can pick for the minimum track spacing of 4 and the track width of 4 and the track spacing of 4. So 4-4 spacing means the track is 4 mils wide and there's a space of 4 mils between each one. You can totally pick that, but the price goes way up. Once you get up to 6 mils, the price stabilizes, and I don't think there's much of a difference between 6 and 8. So it's a pretty good idea. If you go through these little calculators that various PCB manufacturers have, type in your specs and your anticipated length and height and all that stuff, and you can click around on these things, and it will real-time calculate what the cost penalty is of those things. But let's say we want ours to be 8. Just for the sake of discussion. So all of these spacing, every time I click on one of these things, it's telling me, hey, how wide or what distance do you want between this type of feature and this type of feature, like between wires. I'm going to make all of these 8 mils, and you can kind of go through and look at all these stuff. So you have quite a bit of control over these. Generally speaking, with most design rules, these all end up being about the same number. So here we have the the distance tab is how far any of these copper related features can be to the edge of the PCB. And I think that, not positive, but I think that PCB way is 20 mils. So essentially I can have copper go all the way up to 20 mils to the edge of it. After that, you risk having the copper torn or whatever, or they may reject it. And so this one is the distance between drill features. So we'll make this one, 8 mils as well. And I'm just flying through this stuff. Let's see, this one, okay, so this is the minimum width of a line. So the clearance is how far apart they need to be. Over here, I don't want any line to be less than 8 mils. And when I select that, when I go to design the board, it's not going to let me choose anything smaller than 8. In this case, the minimum drill, we can go back to the thing, but I can tell you that PCBWay can do 0.2 millimeter drills, really tiny suckers. But they charge for it, and they charge a lot, and they justifiably charge a lot because it's a pain. So the price kind of stabilizes at 0.3 millimeters. So now I have this thing set up to where it won't let me choose less than 0.3 millimeters. Okay, so the next one, annular rings. This is referring to the copper ring that goes around a via when you drill it. And that copper ring needs to be considerably bigger than the drilled hole because the drill never hits the same, it doesn't hit the exact spot. So that's something we're going to look at in the next video, actually, how that needs to be determined. Shapes. Where are we? Oh, shapes. So let's see. When it's talking about the SMD roundness, it's how it's going to round off sharp corners, which is really important for the screen printing process. And I think that's something that's better demonstrated in the next video. Thermals are the kind of the copper design, I guess, up to a drilled pad that allows the heat of soldering to stay kind of within that pad and not be sucked up into a power or a ground plane. Another great topic for, it's almost an entire video probably, but that's what that means. Let's see, mask. This is a little bit more important. So this is how close it's going to allow the solder mask to get to the pads. And this default that I'm seeing right here is actually pretty decent. Essentially, what it's saying, it's going to do 4 mils, 4 thousandths of an inch away from the copper pad is where it's going to put the solder mask. Which is super important, but a lot of this is defined by the PCB manufacturer. And so as you define all of these little elements, it's a pretty good idea to find the information on the manufacturer's website or contact them for a spec sheet or that kind of stuff, so you know exactly what to pick here. And then in miscellaneous, these are miscellaneous things that Eagle will check during the automated design check. And let's see, checking the font and the angle and all that kind of stuff. Checking I don't know why check stop mask is off. Restricting wire stubs is good. Like if you just have a route that goes nowhere, it might be kind of obscured a little bit. It'll tell you about that. The width of polygons probably not too important, but anyway, so that's kind of the overview of the design rules. I think on the next video I'm going to load up the design rules that I use, and then we can take a look at how at a finished board and how those things impact a finished design and how you interact with this as you're designing it all along the way. So we will see you on the next one.